And this is with the noise power spectral density. We've talked a little bit about this before in some previous lectures. Since it's impractical to analyze noise in the time domain, we turn to the frequency domain. And so in this plot down here, we have what we've called before as white noise. And I've just drawn in here what 1 over f would look like. But we're mainly going to concern ourselves with this noise that's here. And so this random signal gives us this power spectral density. And if you remember, we talked about the Wiener-Khinchin theorem, and we could say that the variance, sigma squared, of this signal could be related to the power spectral density. Do you remember how we did that? We said that if we had a bandpass filter that filtered out a certain amount, the area underneath that curve would be equal to sigma squared. And that's how those two are related. And that's how we go between the idea of noise in the time domain to noise in the frequency domain. And if you're trying to figure out how do we do that, just go back to that idea that the average power for noise is constant. So whether I measure it in the time domain or measure it in the frequency domain, the average power is going to be the same. So really all I have to do is calculate, well, what's the average power? And that is the power spectral density integrated over a frequency. That's going to be equal to the total power of the signal. And n squared over here, which is related to sigma squared, is going to also be the total power. And I can equate those two through the Wiener-Khinchin theorem. Since it's impractical, so this shows in a little bit more detail how we actually calculate the noise. So we've shown our signal here in the bottom, and we're going to pass it through a bandpass filter. Now this just isn't for our calculation. As you've seen in all of our receiver designs, we actually have bandpass filters for a lot of reasons. Some is to select a certain band, some is to select channels within the band, and also it is to reduce the noise, and we'll see how that works here. So what we want to do is we want to calculate the total noise power, and we want to integrate the power spectral density from one frequency to the other. And so what we're going to do is we're going to integrate it over a bandwidth B. And we know it's white, right? So this equation is simply some constant times B. And the question is, how much is that constant? And that's what we're going to figure out next. It's due to a magic parameter called Boltzmann's constant. And so the average power of noise across a matched load for a resistor, which I'll explain in a moment, is measured over B hertz, which is a bandwidth, is given by KTB. And so remember, this is the power spectral density level for white noise. There's T. K is what converts it from temperature to energy. And so this is kind of cool. Now you can really realize that anything that has a temperature that's non-zero has a random motion of its particles, and that can be related directly to what temperature it's at. And so what we're doing is we're just taking that constant and multiplying it by B. So noise power is determined only by T. And if we have a resistor that's generating noise, and if you're wondering how does a resistor generate noise, it's actually all the random collisions of the electrons as they pass through the resistor. And the resistor itself is actually vibrating itself. The molecules themselves are vibrating. And all of this ends up in giving you a random noise. But what's interesting is the noise power is independent of the value of R, and it's independent of frequency. And if you're thinking, well, that doesn't sound intuitive, well, just go back to this equation right here, right? Remember, the noise power is KT. And we know that's a fixed constant. The white noise is a fixed constant. We don't see an R in there. And so let's figure out exactly how do we figure this out. And so this is an interesting calculation method. We're going to take a resistor that's at a temperature T, and we're going to build a little resistor divider R, and we're going to assume that it has no noise, so its temperature is 0. Now, why are we doing a resistor divider? Well, if you remember, if I have some source here, in this case, the source is is the voltage noise, the maximum power is transmitted out of this resistor into a matched resistor. And then, as we said before, we always have some sort of bandpass filter that's going to integrate the noise, and then a power meter on the output. And in case you're wondering, there's our value for K. Another point, T is in Kelvin, because K is in scaled for Kelvin. So let's look a little bit closer at how we get the actual noise from a resistor. We assume that the resistor does not generate noise, and we model the noise as a voltage source with an average power. So I just want to be clear here. It's not that we're saying a resistor doesn't have noise, but it's easier to say, let's take the noise out of the resistor and treat the resistor as ideal, and then we can just do our circuit theory with that voltage. With this model, we can calculate the noise power which is transferred into a load resistor. So this is just a diagram of what I showed before. Here's my noise source, and then I assume that this resistor is ideal and this resistor is ideal. And this together is the actual real resistor. But you can see if we separate it out into these pieces, it's pretty easy to go and do circuit theory. What's the value of the voltage? Well, this is what Johnson figured out for us. It's 4kT R1. And you're thinking, aha, there's a resistance there, R1. I thought you said it wasn't dependent upon the resistance. Well, let's go look at how much power is delivered, because what we measure is the noise power. And so we know that the power on resistor 2 is just V squared over R. And so let's figure that out. We've got our input, Vn squared, and we've got our resistor divider right here. And so all of this is our V squared out, and then we're going to divide it by 1 over R squared. And if you go through the math, sorry about this. This should be 1, 2, 1, 2. There we go. And if you look at this quantity here, you're going to figure out really quick that it's just going to give us 1/2, right? Because R1 is equal to R2. And so this is just R1 squared, and this is going to be 4R squared. And so this is just going to be R squared over And so this is just going to be 4kT R squared over, this is equal to 2R. 2R squared is going to be 4R squared equals KT. Okay? So while the voltage has an R in it, the power delivered to a matched load is just KT. Okay? This is just a derivation. We're not going to use this further in this class. In a circuits class, we would actually do calculations through a circuit of the noise. All you need to remember is that the final noise is just KT as the power.